Well, this is an unusual class in the sense that we're trying to look for something to happen in the future that involves the molecules whose models you see standing around here. And so what I'd like to do today is just get that started by looking at some examples of the spectra that these particular high symmetry molecules exhibit, and why finding that spectra for some of these smaller fellows would let us attack this Mount Everest of molecular physics, the C60, and I'll explain why it is deserving of that name as far as its physical properties, its quantum properties. And while we're doing all of this, we'd like to just give a broad brush view of what goes on to make the materials that we have. In particular, what's different about the kind of spectroscopy that most of the people in this building do, which is solid state physics, and this stuff that we're doing with the molecules. Now, one of the things that we'll have in every one of these classes or lecture slides is on page 2 we'll have links to various papers and books that are relevant for the whole course, for the whole effort that we'll be engaged in here. And this is a rough arrangement. We'll probably make it better as we add and subtract things, but basically the names of the papers that we'll use. For example, the very second to the top, this one is something we'll tackle a little bit later, but this is one of the earliest papers that I wrote with 2 other authors that sets up the group theory of rotation of molecules in a different way than it existed at the time. And we'll be pulling some of the stuff from that. And just to give you an example, I'll go ahead and click on this and see if it works. I haven't tried that in this particular setting, but let's just see what happens here. And it's saying having a trouble finding the site. That shouldn't have happened. Let's see if there's a reason for that.
First of all, enter your cache and then go ahead and look at that full address.
Okay. This is it right here.
Mm-hmm.
Yeah. Let me.
It's reading right from what I can see.
Yeah. Let's do the preferences here, and we'll empty the cache. Where is that? Privacy and security. Doesn't make it easy to find that. Where is
Firefox does have it in a squirrely spot.
Here we go.
Yeah. Clear now. It's optical. Right.
There we go. Clear that. See if that works. Okay, and then let's redo it. See if it will pick that. Doesn't seem to be working too well here.
Do you want me to sit down? I'll clear all that stuff we're not using off.
See if it'll do it on the other machine here.
Check. You could do the scan version if that one doesn't work. Huh.
There we go.
Beautiful.
That's the paper that has a lot of the starting stuff for this. Let me just point out what this thing, started. I just really wanted people to have good pictures of the molecules. So this is where this little device got invented. Okay, this was at Gilla, and I just made that picture of a device that would show the angles that you use as coordinates for something that's rotating. And a very skilled machinist happened to see the picture, and he said, I want to make that. This is Dick Reese is his name, and he went and got, all of the materials to actually build one about this big. It was a great big thing that was sat in the library for quite a few years, and I think it's still around at Gilla. So the problem with it is that I didn't anticipate wanting to have an operator, that's this thing right here, come and rotate that, because if I had, I would have known to make quarter circles for the supports, which is what this has. And so I built this thing at Georgia Tech with the knowledge that I gained by this. In any case, for example, in our second lecture, the one's coming up tomorrow, I want to make sure that we understand this particular formula right here, because almost everything that we do for the theory of this of the molecules up to a certain point, as far as the rotations and the electronic wave functions and some of the vibrational wave functions go, the irreducible representation of rotations, again, alpha, beta, and gamma being those angles right there, those coordinate angles. Those I really want you to be very familiar with, and this is a start right here, which we'll be doing in the next lecture. In any case, that gives us some idea how easy it is to bring up. This is a long paper, fairly long, 70 pages, something like that, that has a lot of the stuff that we're going to be doing, but in a way that is not quite as clear as it got as the years went by. So the idea of making that simpler and more powerful is a key thing here. Okay, well, let me back out of that and return to the lecture, and I'll do the same with this one. We don't have to access too much today from this, so I'll remember that that's the machine that works. In any case, the first thing I want to do is just a rough sketch, a very rough sketch of the idea of molecular spectroscopy and how it meshes with other things. And this is a little sketch that's in another reference that we'll make use of, which is a textbook that's sitting over there, that gray thing on the middle desk over there. It's a textbook on applied symmetry analysis. But the basic idea is that you start off with here the high frequency spectra. That is, spectra is the difference between the energy levels, say of hydrogen. If you had a hydrogen atom, the only thing that would be of interest would be these Rydberg electronic levels, and the electronic motion of that that's gotten by combining more than one level, and it always takes two to tango in the quantum world. That would be operating at frequencies that are, well, very high, and that's the thing I would like you to start to get, if you haven't already, familiar with, thinking in terms of frequency per time, per second. Trillions of terahertz is what we'd be talking about here. For example, if we're interested in, say, 600 terahertz, that's the green light, very close to the green line, half a micron being the wavelength, half of a micron, 10 to the minus 6 meters, is the same as 600 of these things. That's one of my favorite frequencies for reasons you'll see later on. And then, of course, giving these energies in electron volts is another way to express what's going on in spectroscopy. So we'll go through a little bit of this again, just to get you so you can visualize better what's happening in a spectroscopic situation. Anyway, if that's all we had, and that's what I have in the next slide here, if I just erase all these other guys here and just look at the spectra of an atom, then there aren't any but one nucleus. So it's just the electrons around one point. There's a lot of physics in that, particularly if you start doing larger nuclei, more complicated atoms than hydrogen. But in any case, that is a lot simpler than what we're attempting to do, which is allow there to be at least two, or better yet, three nuclei, and then it's the vibrational spectra of those that combines with the electronic spectrum, and that means that for every electronic level, there's a whole bunch, a whole ladder of vibrational states. And at first, for the simplest cases, these are spaced out very nicely, like a harmonic oscillator. Of course, the inharmonicity sets in rather quickly in most molecules, so this is an idealization here. But the idea of having every one of these levels have multiple levels associated with it is part of molecular physics, certainly, but in solid state physics we call these the phonon bands. These are the electronic bands here, and each of them have a set of the other. Each of the bands here have bands that go with the vibrations. Well, that would be the end of the story if you weren't going to let these molecules go free. If you let them go free, then each one of these, which means every one of these things, also has each one of a rotational spectrum to go within. So this is one of the things that makes a lot of people very nervous. A lot of physicists would just prefer to have one nucleus and then a certain number of electrons. Actually, they'd like to have one proton and one electron, and worry about that. This is a long way from that. And then beyond that, and that's where our work comes in, is that these rotational states here can be quite complicated. First of all, even before what we call superfine structure, every one of these right here would, in general, have hyperfine from the nuclear spin, and we'll talk about how the nuclear spins make a lot of difference for our spectroscopy, but it does a little bit. It's behind the scenes usually in most other kinds of spectra. And we're going to be interested in this stuff, which is called superfine splitting. So these are additional things that can be attached to each of the rotational levels here, which in turn are a band attached to each one of the vibrational levels, which in turn this whole mess you see is attached to each one of the electronic states in a molecule. So anyone that has not had some way of thinking about this would say, my goodness, this is an impossible situation to do. I mean, look at all of the structure here. Look at all the things that can happen.
Is there any place in there where we might consider ourselves to have some mastery?
Well,
or perhaps the origin? I thought we started over on this.
Well, that's why I'd like to show you some examples. Okay, examples of hierarchy. That's what we're really talking about here. Really complicated hierarchy is what we're dealing with, and so the question is, how can you make your way through something that's this complicated?
Dr. Can you update the picture? It's because it's really difficult for me to see that.
We'll keep up. This is where we were, and I'll bring it up at this point right there. Yeah. I tried to come in this week to switch projectors so that we get this one over there where we don't, this is kind of dim compared to that one, but we'll get that fixed so we have just as good an image here as we do there. Okay, let's do an example just to get a feeling for this. And this comes out of this look here. Because we figured out this spectrum, we were asked to do a chapter in this American Institute of Physics handbook, okay? And as you can see, I can hold it in one hand, but just barely, right? You've got to play a lot of tennis before you can throw this handbook around. But the idea is this hierarchy is happening in part here. These are several different vibrational excitations, fundamentals they're called. They're an excitation from the ground state to a vibrational level above the ground state. And so what we're talking about is a transition from here to here, or from here to here, or maybe even one between that, but pretty much very simple, one or two quanta of vibration is what we would be used to seeing in all of the spectroscopy that occurred up to 1970, well, probably 1972. You'd be very happy to get a spectrum with that much resolution. But this, with Fourier transform spectroscopy, blows up this thing, and so do the other ones, blows up to this hierarchy right here, where you're actually seeing the individual rotational excitations with angular momentum ranging up to 60 or 70 here. This is 30 and 40 right here. And there's a letter R on that. I'll explain that one in a little bit here. And there's a letter Q representing all of this stuff, all compressed in the middle here. And then on the other side is the P branch, they call it. All the little P's there indicating also quanta of angular momentum ranging up to, say, 50 or 60 on this side right here. So it goes 10, 20, 30, 40, 50. So it goes 10, 20, 30, 40, 50, 60. And maybe even a little further.
Dr. Harter?
Yes.
So is this the total angular momentum J? Or
Yes.
Is it,
yes.
okay, so it's total orbital plus spin.
That's what we're going to be talking about a lot,
Okay.
is what happens when you have a lot of angular momentum, a lot of quanta of angular momentum. See another example of this in just a minute here. It's even more than this. But in any case, this is a molecule that mimics methane molecule. It's called tetrafluoromethane. Okay, so this is the molecule that's doing all of this. It's Freon, very bad molecule for our ozone layer, right? This is Freon 14, very bad. It was used for refrigerant. It was in air conditioners, in cars, all sorts of things. Now we've gotten rid of that, pretty much. We've brought the ozone layer back again by getting rid of this from our daily use. Okay, so in that sense it was a bad molecule because it was destroying the ozone layer, but it is a really good molecule for making clean spectra of a hierarchy. And each one of these angular momentum excitations here can be looked at, in this case with a lead diode, the beginning of the laser diode. This happened in 1972 to the 80s. We could look at each one of these. Well, usually didn't get to pick it because it was hard to make a diode that could go anywhere. But this is an example of an experiment to see what was going on. This is where some really amazing quantum mechanics is happening. And that's what we'll be talking about early on in this course, just to get started. Because this is the kind of things that buckyball will be doing, even more complicated dances in the rotation. But it doesn't stop there.
Dr. Harter, one
We
question.
can look even higher.
So that angular momentum that is displayed on the picture, the numbers 30, 20, 40.
Yes.
So is that
54.
50? So the 54, for example, is that the total angular momentum of
Yes.
carbon and the 4 fluorine atoms together?
Yes, the total angular momentum of the molecule goes down by 1 quantum if you're talking about these. It stays the same if you're talking about all of the ones in here, but we can't look in here, it's too crowded. And it raises. And I used to say R stands for raise, Q stands for status quo, and this is for plummet. Plummet means fall down, okay? That's just my way to remember which ones they are, okay? I love mnemonics because I don't have a very good memory, right? But this guy right here, P54, that means you started with 54 and went to 53 in your transition. Actually, you started with 55 and went to 54 is the way this works out. Okay. So every one of these guys in here has that value, effectively, the value of the angular momentum 54. And then it gets really weird down at the bottom, because now we're starting to worry about how this molecule's angular momentum literally tunnels around to different places in the space of the molecule. Okay, so that's an example of a hierarchy that involves vibration and rotation. Electronics have not changed. This is keeping the electronic wave functions the same. They're acting as classical springs in the stretching and bending and rotation of the molecule. Okay, now the result of doing that over a period of time resulted in another handbook. This one, okay? This particular one is in 2005, and this time it's Springer, German, okay? I mean, this is a two-handed book, right? Just barely lifting it up, all right? It's gotten bigger, but we write more and better pictures in this one, okay? Same picture, but now prettier, okay? So this is 2005, but things haven't changed, but they added a little bit to this, and we'll be talking about that fairly shortly here. And I'm going to go ahead and follow on this screen just to, you know, have some comparisons to make at a later point. Now, come to this present day, okay, 2018. Again, we've been asked to do a chapter in this handbook. So, I added this. Okay. Now this was something that had already been done, but now we understand it better, and plus we have better, more reasons to look at this, because this is the one that shows that C60 is perhaps a doable thing. But it's the same idea. It's the same hierarchy as we were looking at before. The top row is now involving more quanta of angular. We're talking about 88 now. As opposed to 54, but this keeps going. You can see spectra up to hundreds and some and change. And this particular manifold of levels is what's inside each one of these. But this one is way more complicated, particularly when you start looking inside what we call superfine structure. And that's just the things that I wanted to fairly early in this development show how to understand. But anyway, all of these symbols in here represent irreducible representations of the group of the symmetry, in this case octahedral symmetry. A group of order 24 or 48, depending on whether you allow inversions, is doing something weird with those irreducible representations. They're making them come together in clusters that have little splittings that go down exponentially, and that is what makes this molecule and others like it, high symmetry molecules, interesting. Meanwhile, the nuclear spins are having a little bit of a dance, because they're riding on this rotating molecule and responding to those rotations. So the rest of this right here is where we're very much interested in these two molecules, CF4 and SF6, but mostly the weird stuff comes with C60.
Dr. Harter?
That's going to be the
So
main
what
topic.
are the criteria which decide when should you consider superfine structure, hyperfine structure, and super hyperfine structure? Like, are there conditions when you can ignore some of them in your analysis?
I guess your question is, what's the borderline in the hierarchy?
Yeah. So when are there
Right.
certain conditions can you ignore hyperfine and super hyperfine structure in your analysis, in your calculations, to a good degree of?
I would argue that if you're really understanding the molecule, you can never ignore it. But it certainly was ignored because in the early days, this whole thing here would just be one lump, one line. And then we get to look at that using Fourier transform, and then it gets even better as we develop the laser diodes to look at this, and that comes at a price, but we get to do it. And at that point, you do see what we call superfine structure, and that's the next level here. And that takes, that's really hard. Anything below here is really hard experiment. Until recently. Now we have the possibility of using frequency comb technology. And the question is, can we redo these experiments and then we get to look at C60. Probably the only way it's going to happen is with very new types of spectroscopy. So these are names that I just invented to describe something that was finer than fine structure. This is already amazing. This is the so-called fine structure here. And it's just due, well, you'll see what it's due to, but it's due to the molecule stretching and showing a different rotational rate due to its centrifugal expansion. And that's something we have to learn to calculate in order to predict these things. So this is where we get these things. Now, the question is, what might you see with C60? Well, first of all, it's a big molecule, so it's very likely that these high values of angular momentum will be present, even at very low temperatures. And so we went ahead and we calculated, and we'll show you how this calculation is done. It's basically a matrix diagonalization. In this case, I'm imagining J equals 100. I mean, if that one was able to make 88, this is going to easily make 100. But this is the picture that you might see if you could look at C60. All right. At least this is what you would be getting as the first step in doing the theory of the rotational angular momentum, say 100. So what you're talking about here is at the very top here, and that would be the very left-hand side of the original ones that we can see, it's SF6. But if you see the numbers here, the actual eigenvalues that come out from doing this on a computer, here is 11-figure degeneracy. Only the last 12th, 13th, and 14th numbers are different, and they give you a pattern that looks like that. And the idea is to understand that pattern. What does it mean? And these are the letters that designate the irreducible representations of the icosahedral group this time. So it's a more complicated set of group theory, very much more complicated group. It's called, in the mathematicians would call it the alternating group 5. It's the even permutations of S5, which is a permutation. You've probably heard a little bit of this in your math, maybe. But the permutation groups are really important, and the S5 is, this is half of S5 that we're talking about when we look at an icosahedron like that. Or here is a molecule which we will never be able to do. It's not even stable, and it's an ion. This is a boron hydrogen 20. Okay, so you're making an icosahedron there very obviously. The buckyball you see, and if you turn around and look on the shelf up there, I can't do it because the thing falls apart, but that's a dodecahedral molecule made out of carbon and hydrogen, C20H20. This is B12H12 right here. They are out of our reach. We can't make them easily. Buckyball makes itself. It takes an incredible chemist to make that thing. It took 18 years just to make a tiny little bit of it. Anyway, when those things rotate, they make a structure here, superfine. By superfine, I mean ridiculous degeneracy, really close together. You don't see any splitting of these levels at this magnification until about here, where you have a one-figure degeneracy. Okay, so there's an exponential crushing of these superfine clusters in all of these molecules that behave like this. Then there's this weird region we call the Spectroscopy region, where you then get a different kind of cluster, and then you start to see better and better degeneracy, more and more tight degeneracy, two-figure, nearly three-figure degeneracy, sort of matching that degeneracy right there at the end, at the very end of this spectrum. Okay, so understanding this is certainly important. Understanding what's going on with all of these little symbols here that represent the symmetry labeling of the representations of the icosahedron is certainly important. So that's something that we need to do in this class. That's something that is pretty new and a lot yet has not been done yet. Okay, so that's the situation. But now let me point something out here that's really quite remarkable about this, and that is here in this thing using carbon, we have something we didn't encounter before. All of these other molecules that use fluorine as the rotating atoms, no other isotopes of fluorine. Fluorine-19, that's it. Okay. This guy, carbon, has two stable isotopes. The usual carbon-12, very common, and then 1% natural abundance of the carbon-13. Extra neutron, that's the only difference, okay? Well, if I do a carbon-12 buckyball, this spectrum right here will look like that. Let me put it over here just to see it.
Showcase
Okay?
it.
So, what has C12 done to us? Okay? Out of the 100 multiplet, and the 100 multiplet has the substates of 2J plus 1. That's 201 quantum states that are supposedly there, but they're not. Okay, and the question is, where blankety blankety blank did 197 states go? That's something that I want to make clear at some point during this course. Okay, this is really amazing. And the reason that they go is because we're talking about carbon-12 whose nuclear spin is 0. And by being 0, it destroys all of the structures except those ones that have the symmetry that 0 has. And there aren't very many. It's only 4 in this particular case.
So all these 4 peaks correspond to the states whose nuclear spin is 0.
0, right. All those things that are behind the scenes there are gone. They do not exist. Molecule can't make them. So this is beautiful. This is really beautiful. I mean, it's hitting at a principle that's very easy to state. Feynman used to make the point that I can tell you about the Pauli and the Bose exclusion principles really easily. I can just use words that you all know. Okay, and that is If you have a nucleus, or any object has a half-integral spin, then it will form wave functions that are antisymmetric. That's called Fermi-Dirac symmetry, or Fermi-Dirac permutational, whatever you want to call it, okay? And the opposite of that is if something that has an integral spin, that includes spin 0, then the wave function that goes with that has to be absolutely symmetric. Now the half-integral spin, the antisymmetry of that is what gives us the periodic chart with all of the different atoms, and that means all of the different nuclei, because all of the nucleons, protons and neutrons, have spin 1/2. So they're busily stacking up because none of them can be in the same state. So you get to make a rich structure of states by just putting more particles in there and having them go up the ladder, because none of them are allowed to share a room. Okay, it's verboten. But bosons want to share room. Okay, they'll all go down and sit in the ground. That's the idea of pairing electrons and superconductors to make it so that they can all exist in one band, in one state. Okay. Well, the situation with this molecule is it's a Bose molecule if it's C12. If it's all C12, those guys that are in fuzzy there are gone. Only the A species, the scalar symmetric irreducible representation, gets to live.
So, Dr. Harter, just to clarify, is this one the spectrum of carbon-60 with
We
a
don't
combination
have that, but this is what it would look like.
of carbon-60 made with C12 and C13, or is it
12.
only 12? Then what about
Yes.
this one?
This
Well,
one.
The
12.
dark is 12.
C12, okay, has only 4 states. This is what you're seeing here.
Right.
C13 makes up for that.
Yeah.
If it's C13, okay, that's a spin 1/2, which has 2 states each, right? Qubit, right? Okay, a qubit, but 60 of them. So you're talking about octillion states, okay? And then multiply that by 201, and this is how many states you're really talking about here.
Okay, so this is the spectrum of C13.
But 13 will look like this and have these numbers.
Including the gray.
What about C20?
Carbon-20 is really very unstable. I don't think anybody's ever actually made a carbon-20. Is that what you were asking? Yeah.
I could do the ring.
I think the C, well, you could put carbon in a, that's a good point, is that you could put 20 in a ring, but that's a whole different kind of spectrum. We'll talk about that too. That's a very analyzable one. But once again, the difference in the richness of that spectrum from having 2013s and then on the other hand 2012, very different. But this is even more different. You're talking about 4 versus 2.300 octillion states. So this is what we're faced. This is what we face. Now between these two extremes is a whole ballpark of buckyball with 2 13s, which can be in different places. And then after you get done looking at that, there's 3 13s, which can really be in different places, and then 4 13s, and so on, all the way up to 59 13s and 112, and finally, the thing that I'm talking about here, which is 60 carbon 13s in a buckyball.
Well,
And at that point, you get this maximum number of things. So,
what about transitions, though? A to A transitions. Can you see those?
well, these are species numbers, and species, until some funny things happen, are invariant. So whenever a transition occurs, the species is invariant, mostly invariant, until you look really carefully at the hyperfine structure, and then you discover that the species have played footsie with each other within that cluster. And that's something else we have to study, because there'll be a point going along here where you'll make the transition from things where the spins are paying attention to the rotation, and then from there on up they start to pay attention to each other. So there's going to be, you know, different patterns, and that's something that's kind of alluded to in the preceding slide where I showed SF6. This case 1 versus case 2 goes from having species that identify themselves by certain patterns, and then ones that get mushed together and make a completely different set of patterns. It's more like a molecule doing NMR on itself. That's what this really should be called, I guess, if you want to give it a jokey a title. So there is this boundary that's going to occur, and with with the carbon 1360, that's going to be a big deal if we can see it, even for low J's. And we'll be dealing with low J's first, just by necessity, because this molecule has to be cooled.
Well, okay, but I don't know if that totally answers my question. On this diagram over here, you have this dense spectra because you have all of these different types of symmetries. So there's a lot of different possible transitions that can happen and have some sort of visible or measurable signal coming out. But now let's say you take away all the T's and you take away the E's. Then when you get over here to the state diagram,
If you could find some way to filter out the T's by, say, reducing all the T2s so that the T2s didn't show up, that's conceivable that there might be some way to do that. I don't know how you would do that.
well, I mean, it kind of seems like on the right-hand side that's what it would be like, because there are no T states in this carbon with the C60 with carbon 12s over here. There are no T states, there are no G or H.
Yeah, all of these other guys here,
They're gone.
they're gone? You
Yeah.
bet.
So then what do you see in the spectra? Do you actually see transitions for A to A transitions, or are those, can those
Yes.
even possibly happen?
Remember, I said that the species, even if they're certain, I should say, each of these things, each of these species is like a different chemical. That is, you shine your light on it, and it goes up to an extra quantum vibration. Okay, but still, all the patterns that you see have maintained their integrity, and none of the molecules has gone from being a ortho, which is typically an A-type species, to one of the metas or paras, which are all of the others. They are named by their T1, T2, E. That's the most common way of designating the irreducible representations of the octahedral group.
Maybe I'm confused about something here, but I was under the gross impression that if there was going to be some sort of light signal released from a molecule, then that would usually involve,
The transition of the species?
yes, say from A to T or something.
Well, and I think it's probably absolutely correct to call that Hertzbergs Rule. And that is that the rovibronic spin species, that's the full name of the symmetry that goes T1, T2 for our friendly octahedron, okay? The rovibronic spin species are totally invariant. He said that because the nuclear spin moments are so incredibly tiny, and they are, their effects are tiny. First of all, because the spin moment of a fluorine spin and a half, tiny compared to the electron, absolutely tiny, almost unmeasurable. Okay, turns out to find ways to measure anything, right? But it is really down by factors of thousands. Okay, and then the probability that you would have rotation vibration levels that were within that tiny hundreds of hertz, within hundreds of hertz of each other, so they could resonate and actually make a change from ortho to para, essentially zero. The probability. It's about the same as the probability that solar systems in galaxies that are passing through each other actually collide. The galaxy goes all the way through with no collisions usually. There's so much space there. You see, we're talking about orders and orders of magnitude. So that was Hertzbergs rule that the species are invariant. Now, where does this come up? The simplest example is hydrogen. Okay, the hydrogen atom and the molecule. Ortho versus para. One of them has the spins lined up, the other one has the spins opposite. Now the ones that has it lined up, has them lined up to make spin 1. Because they're 2 halves, right? We're talking about nuclear spins, all right? So the one that has them lined up, there's more states. I remember that's like the more popular. It's more orthodox, right? Okay, so ortho state is the one that has more spin possibility because it's spin 1. Okay, and it's a little higher in energy than the para state. The para state is where the spins are opposite, makes spin 0, and that, you know, as an example, that's symmetry that's killing all the states here. But in the case of hydrogen, it's a little bit lower. Okay. Now, what's amazing about hydrogen is that it's like having 2 different chemicals. There's the para hydrogen. You could, you know, put in a bottle and it would stay para. And then there's the ortho, and you can put it in a bottle and it pretty much will stay para. And then you can mix them together and the paras and the orthos will be in that bottle, but never will a para change to an ortho. That's amazing, right? I mean, that was a thing that everyone sort of knew that it was true of hydrogen until one day it blew up. And this is where Guchnet figured out about spin. What happened was they were storing hydrogen in big iron containers, and the iron has a magnetic moment. So the iron's magnetic moment could grab onto one of those orthos and kick it down to para. And every time it did that, it gave a little bit of energy to that bottle of hydrogen. And then it happened again and again and again. The bottle started to get warm, and then it got warmer, okay, because it happened more. And then it started to boil, okay, and the hydrogen has this weird thing, it's called inverse boil temperature. That's B-O-Y-L-E, and what happens is when you expand it, you heat instead of cooling.
Yeah.
So it started to expand, and it blew up. It set it on fire. And this was happening in World War I, in these huge vats of hydrogen to take care of the dirigibles. Okay? And they thought it was sabotage. They're going around looking for the Germans to, you know, blow up the things. It wasn't. It was ortho-para conversion. This is one of these little known things about this thing. So that's an exception to the idea that the species are inviolable.
It takes a mediator, usually, to change
Yeah,
the things, right?
outside effects can change para to ortho, obviously. You get it in a microwave cavity, you have a transition between ortho and para. Okay? So, now, what's interesting about all of this stuff is that Hertzbergs rules end about there. And the reason for that is that as we lower the splittings of this superfine structure, as we lower that down to, say, 12 kilohertz and start to get into the single kilohertz or fractions of hertz, and finally it's really gone by this time. Because now these species are so close to each other that now they say, hey, you know, I've got a bigger spin than you, I might give you a little bit of it. And so all of these things lose their designation of being a separate E, a separate T2, a separate A2, or two T's together, or so on, they lose that. In process of making something new, which I call case 2 clusters. So this is a second example of a breakdown of a rule that was really held for a very long time. We were the first to point this out.
Is it part of your 1981 physical display
Yes.
article? Okay.
You bet. Yeah, that's this guy right here. Yeah. Speaking of which, we might as well see if that one will light up. No.
Your internet on that laptop is down.
That could explain it.
You never verified that, or at least
Yeah.
it could have bounced on us.
This is what I wanted, and I thought I got it going, but it didn't. Let's go ahead and pull it up on the one where the internet is working. That's the disadvantage of the modern deals here, is you really do have to bring your stuff to the table. You can't necessarily rely. I don't know why that thing is behaving so. There we go. Let's see if that one will bring it up. Yeah, here it is. Okay, so this is a paper that we'll be looking at shortly, but one of the things you'll notice right away about this thing is, there it is. Okay, that's the thing we were looking at. This is the first figure. Okay.
Oh, it's a long
So
page.
the rest of this is just talking about how the vibrations swing the nuclei. We'll talk about that later on.
Well,
And,
funny, a number of them are fairly
Here's
large.
the actual transition diagrams to make P, Q, and R branches of the thing.
That's your paper, Dr. Harter, right?
Yeah, yeah. And this is the thing we're really proud of, and it doesn't look like much because this is almost the first example of it. Rotational energy surface, which makes sense out of the crazy stuff that's going on here in the going from here to here. What makes all of these tunneling splittings here is tunneling from various parts of that figure there to other parts. So you're talking about the tunneling of the angular momentum vector of the whole molecule as seen by the molecule itself. An inside job, so to speak. Okay, let's go back here.
Dr. Harter, once could you briefly explain what is meant by tunneling of angular momentum vector? Just what does it mean?
The angular momentum of a flying object, okay, including this molecule, is a vector imagined to be, certainly if you're doing it classically, but also to a certain extent, quantum mechanically, a vector that's fixed to the stars, okay, fixed to the laboratory, all right? And what's going on here, according to the observers of that vector, is that if they started off here, after a while it tunnels over to here, and that means their molecule is actually turned over, right? Okay, but they don't know that, although they should, because they're getting sick to their stomach from riding this damn thing, right? Okay, and then over to here, and then over to here, and so forth. So there's a dance of the angular momentum from fluorine to fluorine, okay? Or if it happens to be on this axis right here, then it dances between those places. Now it has 8 places it can go, okay? So in a picture like this one right here, if you remember what T stands for, it stands for triple. That means triple degeneracy. This one is also triple. So that's 3 plus 3 is 6. This one consists of a double, that's the E without the centerpiece, okay? And then T2, that's a triple, and then the A's, they're always single. Okay, whether they're A1s or A2s, they're both single. So this one is 1 plus 3 plus 2, 6. there's 6 again, and there's another double, triple, single, that's 6, okay? So those correspond to all the possible quantum orientations of this object here that's got that figure. Now this isn't the one that has that picture. This paper is the one that has that picture, and we'll be seeing plenty of those later on. But the idea that the angular momentum can tunnel within the frame of the molecule, as seen by the molecule. Stated another way, the molecule itself can tunnel between rotating there to rotating here to rotating there and so forth, and is doing that. In fact, it's in all of those states at once in order to make an A species or a T species or an E species. So there are these 5 different kinds of chemicals that have different arrangements of the wave of the angular momentum in their body frame.
So Dr. Harter, so does it mean that what is rotation in the lab frame is basically tunneling in the frame of the molecule?
Yeah, if you're on board the molecule,
Yeah.
and you could see the angular momentum, measure where it was, and you forced it to be in one of the axes, it wouldn't stay there. It would tunnel over to the neighbors, and then tunnel down to the bottom, and then tunnel back to the neighbors, maybe with a different phase, and come back to the top. In other words, the whole dynamics associated with the wave that describes where the angular momentum is. You can see why this stuff took a long time to catch on.
See, you know, like,
Abe Zilke at Gilla, when he saw this, and Abe Zilke is one of the smartest guys I mean, he built a whole 2-level system that gave us all of these Rabe waves that every one of the lasers uses now. I mean, he figured out all of the fancy Stokes transformations that Ming Chao works with in his laboratory, or all of the 2-level system effects, lambda transitions, all that kind of stuff. Just brilliant guy. Okay. He looked at it and said, boy, that's interesting, but I'm going to have to wait till my next life to do this. So he never looked at it. He says, in my next life. Okay? So don't feel intimidated if it's, you know, just seeing this for the first time maybe, or really trying to understand it the first time. It takes some difficulty. It's, you know, it's weird. It's not in the usual quantum books yet. It's in mine, but it's not in the others. Okay. So this is just an incredible piece of quantum mechanics going on here, and we're hoping that we're going to get to see it in the big molecule. The question is, how would you ever do such a thing? Maybe we don't do it, right? That's the way it's been for 20 years. But I'm having my faith in particular in Jun Yi's ability to make something happen. Okay, let me back out of this one. And go ahead here a little bit. Now there's some secretarial work that we should do before we close today. And
okay, sorry, I'm still confused
Yeah.
slightly about this last slide.
this
It
one.
says something spectra of C60, but isn't this just a level diagram?
yes.
This is just a level diagram.
Yeah, so then I'm then still wondering, has anybody
Yeah.
made the prediction of what this spectra would look like? Or I guess I'm assuming it hasn't been measured.
Let me put this one up.
I don't believe anybody's actually done that, where they just geometrically projected that from one to the other. You know,
But your
using
question
our
applies to the other molecules too.
Could apply to any molecule.
Yeah.
It has been done.
So let me show a picture using the machine that will give me a picture of that, and that means that we go to that paper that I had here just a minute ago, the one that has this thing. So let me go back to this paper right here, because I don't have this in the talk yet. But let me go ahead in this to a point where I can show you
I think you,
what's going on here.
I think you clicked past one.
Did I go past it?
Yeah, go back about 3 slides.
Yeah, you're right, because I'm only looking at
Right.
the top half.
One more.
Yeah. Now, this is a diagram of how you get the energies by looking at that thing, but I need to go up a little bit here. We'll just scroll through this
That
way
was
so we
an
don't
error.
miss it.
I thought I saw it, but I wasn't.
This is
There
where we
we
go.
go.
So we're looking at this spectrum, and this is the way to look at spectrum. Okay? And this is another thing that was in that Reviews of Modern Physics paper. I could never figure out why spectroscopists would draw pictures with levels here, levels here, levels here, and then draw lines between them. That's called a Gaussian diagram of transitions, right? But you can't tell which lines go with the spectra that you're going to see. Unless you're some kind of genius and can measure the length, right, and put it on a piece of paper. This is the way to do it. Here's your excited states. There's your ground levels right there, okay? That's the spectrum. And the only thing that's allowed is for these particular cluster here to talk to the one like it down here. And then this one talks to the one like it down here, you see. So as long as the rotational energy surface is the same shape for the ground state and the vibrationally excited state, which is what's giving me this spectrum here,
Dr. Harter,
then all of the transitions are pretty much up this line right here. And you just draw a 45-degree line from that and you get the differences between these levels and those levels.
what does N stand for? J
N stands for the internal local angular momentum. And it ranges from, in this case, 88 to minus 88. So this guy down here has N equal 88, 87, 86, 85, 84, 84. And that takes care of angular momentum around the valley, around this threefold axis. Then there's this weird region right here, the Spectroscopy region, where you go out and now you start counting angular momentum off the mountains. And again, it goes 88, 87, 86, and that goes all the way down to about 72 or 71 and disappears. So you don't use all of the Z components, because you have two different Z's to work with, of this angular momentum 88.
So is there a line for the separatrix on this left state diagram over there?
Right about there.
Right there.
Yeah.
Okay, then now I guess I'm sort of starting to understand. You get two of these things, and if we're comparing this one over here to what this one would look like, there would be way, way fewer lines on for the 12C60.
Yeah, this has got enough, right? 2 times 88 plus 1 basically lines. Well, not quite that, because the energies of some of these are determined by nuclear spins.
But then on this diagram over here, the letters for the symmetry states,
Much more
they
complicated.
don't play a part in this particular diagram. Only when you get to the more fine structure on the subsequent
If
diagrams.
you
do
blow
see
up
the
this
letters.
transition right here,
Yes.
you get to see a T1, E, and T2.
Yes.
And you get to see something also that's very interesting about this, which is not written here, but will be written when we go over this one later on. But that is that you actually see transitions now that are off the diagonal. And that's because 2 lasers were used to get this spectrum. So you really need to do a diagram like this to show people what happened during your experiment. And we will really have to do this diagram when we use frequency combs, because they're all going to be doing different kinds of transitions. So this is really old. This is 81, okay, but still, it's something that is worth pointing out. Okay,
So then, do you think that this 12C60 spectrum is not as interesting to measure? Or what would be...
No.
Great place to start.
Let me rephrase that idea very quickly here. Rather than being angry at this, I mean, damn molecule, it took my 197 states, I want my money back.
Yeah.
Right? Instead of doing that,
That's what I'm thinking.
yeah, give me my money back. Right? No, this is a godsend, to use old-fashioned language, right? This is a godsend because the spectrum for this thing is going to be so many lines, so occluded that it's first, you're never going to be able to get the constants. And that's what's happened. Basically, people take the spectrum thing, besides destroying the Kit Peak spectrometer, because buckyball makes crystals that destroy optics. Aside from that unfortunate happening, the spectrum is just like this. You can't see through it. It looks like a field of grass that's thick. This opens it up. This is going to make it doable so we can get the constants for C1260 and have a nice simple spectrum to look at.
But then the downside, do you lose the symmetry sequences A, T, T?
They're gone.
They're gone. So that's a
Yeah.
downside.
You've got to go over and get to 13,
Right.
and I mean 60 13s, in order to have symmetry.
Right.
But there are going to be a whole bunch of molecules that just have 1, 2, or 3 neutrons. They're going to be interesting too, and that was what TC's thesis was about partly, was looking at how the dynamics changes for those. Just because they're not quite as symmetric doesn't mean they should be ignored, right? That's racism.
We love diversity.
You all have to be perfect, or I'm not going to look at you, right?
Oh, so cruel, beginners.
Euchemics.
Yeah, right. Euchemics instead of eugenics. Yeah. No, they will be really interesting, I think, but very hard to look at because all the species start to come back. We'll put one neutron on that, and you've marked an address. You've got a road map that you can make. At least nature does. So it will know about that spin and destroy the symmetry, of course. Now you'd be talking about whatever that symmetry is, and that symmetry is CH. It's not even a rotational symmetry, it's a reflection symmetry. And that's something else we should be talking about later on. So
this proposed measurement you're talking about, it's for 12C60?
got to start. Yeah, but what I'm saying is, I'm hoping that the experimentalists will, take a good look at these now. It's really hard to take the spectra the way these were done. The saturation absorption spectrum, with which that comes from, involved a tube 30 meters long, about 4 or 5 feet in diameter, wrapped with magnetic ribbons, as current carrying ribbons. It had tiny currents in it to counter the Earth's field. It didn't want to have any magnetism to split, Zeeman split this kind of spectrum. This is a Bordes, University of Paris, 17, in Villetaneuse, I think, or some city, it's an industrial city in France. So they got the money from the French government to build this huge lab in a warehouse and study the really fine, hyperfine, and super hyperfine spectrum of SF6. And we're just getting around now to reporting it in their Handbook here. Okay, but that is not in this one. It's going to be in the one that's coming out in a year or so. So we're in the process of turning in our articles in a few weeks. Okay. And then asking, what about C60? I mean, that's part of the gist of what we're writing in this particular chapter of the next handbook. Now, is the next handbook going to be as much bigger than that one was? That means it would probably be about this big.
Tell you what, the new materials, they might have something a little lighter.
Well, and that's the TC is pointing out that one of our chapters, chapter 0, which I'm trying to talk the editors into taking, which does the relativity stuff, okay? An elementary optical lattice that gives you relativity and quantum mechanics, okay? That is going to be, and you can go ahead and play with it yourself. The idea is that CD or DVD comes with the book, right? You can put all kinds of stuff on that. That has movies that show how relativity and quantum mechanics work. So we'll spend some time with that later on. But I wanted to get over this hurdle of getting you so that you can be conversant with the spectroscopy that we're talking about here. Now, we're over the time, but I would just like to show you what we still have to discuss is just getting used to the numbers that we'll be talking about for spectra. So we'll do that first time coming there. And we were talking about what, since it's so cold now, we're talking about what temperature it is that a centigrade person.
-40.
Right, a centigrade person, if it was -40 out today, it would be -40 for the Fahrenheit people and the centigrade people, right? It's what you mathematicians call fixed point, right?
Oh yeah, for tractors.
Yeah.
Linear intersection, that's what I would call it.
Yeah, right.
Because the things have different slopes and
Yeah.
different y-intercepts for the freezing point.
Yeah, and then it's impossible to get a fixed point for all three. Celsius, Kelvin, and forget it, right? That doesn't happen. But centigrade and Fahrenheit does happen. Here we have one as well. Might as well show it to you now. I mention it right here. I call it joking. Okay, these are terahertz, 750 terahertz. That's a very striking blue, but it has a wavelength of 400 nanometers. Okay, at the other end of the visible, we have about 450 is pretty much the limit, but 429 terahertz. That's 700 nanometers. Okay, so you got long wavelength, short wavelength, high frequency, low frequency, right? What's interesting is right in the middle of the visible, 548 terahertz is the same as 548 nanometers. So that's the fixed point for the conversion between nanometers and terahertz. Now, how does that play into this little scenario right here?
Questions on that?
548 is very close. It doesn't, I mean, nobody knows exactly where our peak of our visual spectrum is. But if you just look at the clothes that workmen on the road wear, it's pretty close to 548 nanometers. And if you grew up with slide rules, you know that some of the best slide rules were colored that way because it was easier to read. That's the peak of your visual acuity, right in the neighborhood, obviously, okay? And we evolved around that. That's why visual acuity, that is the peak of the terrestrial solar spectrum.
It reaches the surface.
Yeah. It's about, 550, that's what people used to think. But 548 is pretty much the same, okay? And that's the the joke, right? And then I ask a question. Does this prove intelligent design? And the answer is, of course, maybe for some. Okay. And the other thing I should point out here is there's a huge infrared window. Okay, this is right at 10 microns, which is the CO2 line, main line. The one that poor Day was looking at to make that spectrum was 10 microns. Okay, so 10 microns right there. That's 1,000 inverse centimeters. That's the other unit you got to get used to. That's where you do per space. Waves per meter or per centimeter. Okay, that's 1,000 waves per centimeter is an infrared right in this region right here. Okay. Then it's blocked for most of the spectrum is blocked. But fortunately, down here in the radio, it's wider. Until you get to really long waves, then it's blocked again by the ionosphere. So these are, you know, got to realize molecular spectra, main application is astrophysical. Okay, we'll quit right there and take up this on Thursday and talk more about models that we use for molecular physics. That's what the rest of this is. You might want to go ahead and take a look at it on the web.
So, Dr. Harter, will you be posting the lecture slides on your web page?
You bet.
Okay.
And they're already there.
Was the link included in that emailing? That'd be the easiest way.
Yeah.
I don't think the link was included in the email.
But there is a link for the papers.
Let me go back here and see if I got it in there.
You just substitute in our
Yeah, here.
URLs. Excellent.
That's the website front page.
You just click them and it'll navigate you out there.
It should. Let's see if it will by looking at it on this computer.
If you're connected to the
So
internet.
I just go to Harter-Soft, right? That's where I go.
Yes, we'll have all of it set up. You could search, soon you'll be able to search YouTube and find all of it that
Yeah.
way.
Oh, no, not the videos.
Yeah.
Yeah.
Here.
Textbook.
The textbook,
Lecture slides.
here you
Oh.
go. We'll look at the URL once it's launched. That's
Yeah.
the easiest way.
Yeah. Let me see if I can get on it. Ready? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Click. There we are. Okay. Now that's the front page, right?
It's the massive trove
Yeah,
of
this
resources.
you can get anywhere in the website using this. Now, I may be wrong, but is 2018 on here yet?
No, but we can get there real quick. Do that last link that ends in CTCA. Quantum theory for a computer age. Hit that one. Nope,
Wait a
up
minute.
3. Up
This
2.
one?
Yeah.
Okay. Hit this one. That's the actual textbook that I had hoped to be our quantum
And now we
text.
need to replace the 4 letters in the URL with AMOP.
Okay. Let's see if I can. Do you want to come up and try that? So
I got it in my head. And it's sort of cramped here. We got to play games with each browser being a little different.
There you go. There you go. Keep going.
Okay, so AMOP, caps,
Get rid of the QTCA.
and then turn this to web. How do I get it? All right. Looked like the same front page. We haven't
Yeah.
put this semester's
Yeah,
title
but
page in there.
that is the front page for the current thing, right?
Right, yeah.
And
So
here's the lectures right here.
text at the top.
Yeah, there's
The
lecture
lectures
one.
will stack up here. Here's the one we were just looking at.
Okay.
You open the link in a new tab.
Yeah.
Actually, that's something that's hosed from before. When we have our assignments, they'll be in this section. I'm going to go ahead and echo the links that he has on page 2 of each of the lecture notes. It'll be echoed and aggregated here. So that'll be a master list that will eventually be searchable across every piece of information in the site. That's where it's headed. Right now, it's kind of tough because we have like 6 different versions of the same paper out there.
Yeah, there's the actual thing you got from the web.
It finally fit
Just
through.
What we're looking
It's a
at
little
right now.
large.
Yeah. And then you can go down and reference back through that, which
Yeah, see?
gets you tangled up pretty quickly. Yeah.
But we'll go ahead and put it in there the next email too.
Sure.
Just top, top, top. And there's a more detailed page, just like we had before. We'll show you that later on, but and then all the applications are linkable from there as well. You just have to go towards the bottom.
Okay, well, this will be running next time, but the basic thing I'm showing here is the simplest example of tunneling.
So linear
You can see
versus
this wave function
rotational.
is oozing
That's what I would.
over to this side.
It's
Ever so
neither,
slowly.
right?
And it's a resonant process because this phaser set here is 90 degrees ahead of that one. And as long as it maintains that phase relation, it keeps pumping this one up at its expense, which is cool. I mean, that's the old coupled pendulum thing, where one pendulum's doing this, and finally it gets this one going, right? And then this one changes phases so that it can get this one going again, and then it repeats. So that's the kind of tunneling that's going on, but it's happening with an angular momentum in the body frame. And it's not just going between north and south, it's going east, west, up and down, all 6 places, or all 8 places if you're in the between. So it's an incredible piece of quantum mechanics that more people should know about. It's, you know, it's not trivial by any means.
No, I see it better every time I'm exposed to it. Truthfully.
Yeah, so that's to be compared with this one over here. I think I can do. If I mix the two states, that's all it's doing here is we're mixing the two states, the symmetric and anti-symmetric states. If I do the same over here, put a little bit of phase on that one, so that about 50-50. Then it oscillates back and forth in one half period. Whereas this one it takes quite a few oscillations to make its transfer from one side to the other and then back again. That one does it at exactly the transition frequency between these two levels right here. So it's a beat phenomena, which is all there is to quantum motion. It's nothing but a beat phenomena. Everything that happens in quantum mechanics is a beat of some kind. This is very slow. You have to realize there are nuclei that take thousands of years to go from one side to the other. They're sitting there going for thousands of years. Thousands of years. And all of a sudden, one day, it's your day now, pow, you become a new nucleus. And your alpha particle goes flying away. Isn't that weird? So we're talking about orders and orders of magnitude of different timing in these physical phenomena that we are dealing with here. Well, with these molecules, it happens in one spectral line. One end of it is 1,000 years, and then in the middle, it's megahertz. That's what makes this whole business really powerful in some sense. The orders and orders of magnitudes that reside in the mechanics of even a simple molecule like this, even methane.
It's a precision instrument on both ends of the scale if you just learn how to use it.
Yeah. Yeah, it's a long learning curve. Yeah. It's knowledge that has to tunnel. It doesn't just go boom. Okay, well, we'll figure out the timing. Email me your non-available